On the left side of this split screen, a consumer GPU is struggling to generate code at less than 2 tokens a second. On the right side, the exact same hardware produces a blur of over 40 tokens a second. The stall on the left happens when users load massive 35 billion parameter models onto a 16 gigabyte graphics card. The model's data overflows the GPU's high-speed VRAM and spills into slow system RAM, creating a performance cliff where the system simply cannot keep up. You can eliminate system RAM spillover. By precisely configuring memory parameters, using quantization and flash attention, you can hit 40+ tokens per second on the card you already own. Running local models at these speeds on consumer hardware is a software configuration problem. Here is how to fix it. Step 1 is intentional right-sizing. You have to select a model that physically fits on your GPU before you feed it a single line of code. This chart represents a 16 gigabyte VRAM limit. A 35 billion parameter model consumes 20 gigabytes of static weights, breaking the hardware limit. Dropping to a 14 billion parameter model shrinks that footprint to 8.5 gigabytes, leaving a large green space. That leftover space is strictly required. Your system needs it to hold the dynamic memory generated during actual prompt processing. If you leave no room for that dynamic memory, the GPU is forced to pull data across the PCIe bus from your system RAM. This hardware bottleneck drops generation speed by nearly 30 times. A model's high benchmark score on a leaderboard offers no advantage if its physical size forces your hardware into a continuous latency loop. That dynamic memory is called the KV cache. Every time the model reads or generates a new token, the cache grows. To control it, set this specific environment variable to compress the KV cache down to 8-bit integers. This precise setting drops the cache's memory footprint by half. You effectively double your available context window without causing any noticeable loss in coding accuracy. But you have to avoid the flash attention trap. Whenever you use a quantized cache, you must explicitly enable flash attention. If you skip this step, the engine has to dequantize the math back to 16-bit floating point on every single generation step. The extra processing cost results in a system slower than if you had used no quantization at all. Software-level memory compression requires hardware-level computation shortcuts to yield an actual speed advantage. Step 2 targets semantic failure. Automated agents frequently dump entire code directories into a single prompt, creating an unnecessarily massive context load. This U-shaped graph plots attention against context length. Models assign high attention to the beginning and end of a prompt. The middle drops into a dead zone, causing the model to ignore instructions because it can no longer see the data in the center. To physically prevent memory overflow and force focus, set a hard limit on your context window size. Then, manually curate your inputs. Restrict your context strictly to the 2 or 3 specific files required to complete the immediate task. Aggressively restricted context windows prevent semantic hallucinations. They keep your critical routing logic and schema definitions out of the model's cognitive blind spot. Step 3 is execution. Prepare your testing environment by opening 2 side-by-side terminal windows. In the first terminal, launch the NVIDIA SMI monitor to track your memory usage in real time. In the second terminal, launch your 14 billion parameter model with verbose logging enabled. Look at this UI mockup of the NVIDIA SMI output. As text generates, actively monitor the VRAM gauge, making sure it is hovering safely at 10.2 gigabytes out of the maximum 16. As long as that memory metric stays below the 16 gigabyte threshold, your system is operating at its maximum speed. Live monitoring is the definitive proof that your model is successfully contained within the GPU's high-speed memory. With the KV cache constrained and the context focused, the local model outputs correct, unhallucinated Python code instantly. The verbose terminal output confirms a generation rate of over 40 tokens per second. A struggling 4-minute workflow full of errors drops to a clean 3-second execution. A 14 billion parameter model, fully contained in fast VRAM, outperforms a 35 billion parameter model that spills into slow system memory. Check the video description below to copy the exact bash script used in this tutorial and start running local models at their true capacity.